Thanks for sticking with me through what is now the 23rd episode of Lessons with Lenny. This is the third and final part of a really cool story about vaults and how they've been used for environmental remediation. Today, I'm going to address the problem of protecting the vaults from the harsh conditions that they will face in the environment. I already used the waiter serving tasty vaults to diners to explain the problem with feeding vaults to cells, and in a number of ways, this applies to sprinkling vaults in contaminated soil or adding them to contaminated water, as these situations would also encounter microbes that could feast on the high protein content of the vault. So, because I'm running out of ways to grab your attention, I'll just show you another version.
May I interest you in a delicious vault hors d'oeuvre? They are high in protein and completely fat-free.
Hi, I'm Lenny Rome, the Vault Guy. I'm a cell biologist and a nanotechnologist. My passion is a common particle of the human cell called a vault. What I'm trying to do in these lessons is to teach some cell biology to non-scientists by telling the story of the vault particle. Today, I want to cover three things. First, I'll review my concerns about adding vaults to contaminated water or soil, and I'll explain why this might not be a good idea. Second, I'll introduce an interesting material called a sol gel. And third, I'll describe our efforts to protect vaults using this technology. Stick around. You might be surprised by the resiliency of the vault. In the last episode, I told you how we collaborated with Shally Mendra's lab to scale up vault production using yeast. However, solving the production problem was just the first of two big challenges that we faced. The second challenge was protection of the vault itself. The vault that we produced to degrade an environmental forever chemical is still just a nanoscale protein particle. Sprinkling a vault on some contaminated soil or adding vaults to a contaminated water supply means subjecting those particles to numerous harsh conditions, including high and low temperature fluctuations, extreme variations in pH and salt concentrations, and digestion by soil microbes. So the next piece of the puzzle that we went after was protecting the vaults themselves. And again, this work was headed up by Shally's graduate student, Meng Wang. The key to solving this problem turned out to be tied to the NERT grant I described in episode 14. One of my fellow nerds from the nanoengineering NERT group was the legendary material scientist Bruce Dunn. Among the many interests of Bruce's lab was his work on silica materials, including sol gel composites and mesoporous silicates, which are glass-like materials widely used in civil, chemical, environmental, and biomedical engineering fields. A decade before I started working with Shally, Bruce and I had blue sky conversations about encasing vaults in these materials. Fortunately, I continued to be friends with Bruce as he helped establish the California Nanosystems Institute, CNSI, the current home of my lab and the cool equipment I've been talking about in all these lessons. Meng, Shally, Bruce, and I decided to collaborate on encasing vaults in silica. Under Meng's deft hands and help from Esther Land in Bruce's lab, the work proceeded rapidly, and we were able to develop a method that could entrap vaults in a form of silica called a sol gel. Let's spend a minute on sol gels. Sol gel technology is a wet chemical method used to make solid materials like ceramics and glass. The process starts with solutions containing small molecules like silicon or titanium. We used silicon, a chemical element with the symbol Si. Silicon is a metalloid, meaning it has properties between metals and nonmetals. Silicon is the second most abundant element, making up about 26% by weight of the Earth's crust, most in the form of sand and quartz. In order to explain how we make a sol gel, I'm going to show some chemical structures. Bear with me. I'm trying to help you visualize going from the nanoscale to something you can actually see, like a grain of sand. Trust me, the chemical structures will not be on the final exam. To make a sol gel, we start with a form of silicon called TMSO, for tetramethylorthosilicate. This form of silica, which is widely available, has 4 methoxy groups bound. The first step to forming a sol gel is a hydrolysis reaction where the methoxy groups are replaced by OH hydroxyl groups. These silicon hydroxyl groups then undergo condensation reactions to form a silicon-oxygen bond, SiOSi. The byproduct is water. As condensation progresses, a network of connected silica atoms forms, resulting in very small particles that stay in solution. These are called colloidal solids. Continued networking and cross-linking of these small particles causes the system to lose fluidity and become a sol gel, a rigid, porous, three-dimensional network. Meng worked out the conditions for the sol gel formation so he could add vaults to the solution during the condensation. The goal was to entrap the vaults inside the sol gels. It turned out that the vaults served as sites for the silica condensation, meaning the vaults themselves triggered the silica to come together. This process was very efficient, as nearly 100% of the vaults that he added were immobilized in the silica sol gels. We looked at the sol gels that were formed under the electron microscope and saw large amorphous particles big enough to contain a few hundred vaults sandwiched loosely together. These particles were about 1/10 of the size of a fine grain of sand, and on close examination, they looked like they had some cavities embedded in them. These cavities were about the same size as a vault, and to illustrate this, I've superimposed some blue vaults over the cavities. Meng figured out a simple way to prove that the vaults were entrapped in the sol gels. He did this by treating the sol gels with a basic solution, around pH 9. Under this condition, the silicon-oxygen bonds are broken and the sol gels are dissolved. Meng could then recover the entrapped vaults, and he showed that the particles were structurally intact. In episode 21, I told you about the enzyme manganese peroxidase, MNP, that can degrade the toxic chemical BPA. When Meng used vaults packaged with MNP to form the sol gels, the ability of the enzyme was even better than the free vaults packaged with MNP. It turned out that the sol gels acted as protective shelters to preserve high enzyme activity and excellent protein stability. Here's one example. Meng measured the enzyme activity of vaults heated for 30 minutes, comparing the sol gel encased vaults to the vaults not encased. The blue bars represent the vaults encased in sol gels, which you can see significantly preserved enzyme activity. At temperatures above 45 degrees centigrade, the vaults surrounded by sol gels retained activity, while the enzyme inside free vaults was completely inactivated. The sol gels are very porous, allowing solutions containing small molecules like BPA to filter through and react with the vaults. Meng used this property to show that the sol gel encased vaults were reusable. The MNP enzyme retained over 90% of its activity after 30 reuse cycles. This property would be valuable in a broad variety of medical, industrial, and environmental applications. I hope that someday we could just add some vault sol gel powder to water contaminated with a forever chemical, Let it sit a few minutes and just filter out the sand-sized particles, resulting in pure, uncontaminated water. If you're wondering when Vault technology will be applied to environmental problems, I'm afraid that's a difficult question to answer. The distance between demonstrating a promising technology in the laboratory and developing an effective commercial product can be quite vast, requiring millions of dollars of investments. Currently, Shally is writing grants to continue our environmental remediation work, and we are talking to companies that might be interested whenever we get the opportunity. I'm Lenny Rome, the Vault Guy. In my next lesson, I'm going to describe our experience using vaults as vaccines. So stay tuned, and remember to like and subscribe.